Alright, everyone. Doing FRQ number 2 right here. First question asks to plot the points on the table, on the graph. So I have copied it here. So I would like to make the graph right now. So change the color real quick. So my axis is going to be the T, and this is going to be the force, Fn. This is in seconds. So I would like to label this as 1, 2, 3, 4, and 5 because of the 5 points they give us on the graph. And then I'd like to make the y-axis 20, 40, 60, 80, and 100 because it's also like the simplest way to represent the data. So the first point starts at 100, 0, 100. Second point, time equals 1, force is at 80. Time at 2, force is at 60. Time at 3, force is at 40. Time at 4, force is at 20. And time at 5, force is 0. So draw a line through there. And that's basically the graph for part A. Okay, part B. Alright, switch color real quick. Part B asks derive a function for f of t in terms of time. So f of t, it starts at 100, and then it decreases by increments of 20 for every time. So it's just 100 minus 20t. And that's the answer. Part C asks us to find a function for the acceleration, but the acceleration can be found by saying net force is equal to ma. So net force over m is equal to a, but in this situation the mass of the object is 5, so you could just say net force over 5 equals a. So essentially we should take this equation, divide everything by 5 to find a. So a of t equals 20 minus 4t. And yeah. Part D asks for acceleration versus time graph. So part D, let me paste that graph from before. Get it in center. Okay. Change color. So 0. So now the time is still gonna be 1, 2, 3, 4, 5. Let me label this axis real quick. A of t and t on the bottom. And so the axis is, it starts at 20, and then this is 16, 12, 8, 4, 0. So like before, time equals 0, the acceleration is 20, and so it just decreases by 4 every time you go up 1 second. So the line, go through it, something like that. Yeah, that's the graph. Part E asks what information can be extracted from this graph, and so one thing you can tell from this is that since the acceleration function is a linear mx plus b straight line, you can tell that the velocity is a quadratic. And another thing you can tell is that velocity is increasing on 0 to 5 because the acceleration is positive and the velocity is always also positive, or they're both pointing in the same direction for the first 5 seconds. So velocity is increasing on this time period. Part F asks for the a function for the instantaneous velocity at time t. So the acceleration function was let's see, 20 minus 4t. Integrating acceleration gives you velocity, so I would integrate this. So I would get 20t minus, so I would add 1, so this would be t squared, and I would divide that, so it would be minus 2t squared plus c. But then I'm just going to assume that c is equal to 0, so I'll just get v of t is equal to 20t minus 2t squared. Yeah. Alright, so for part G, I'll use the fundamental theorem of calculus. Oops, I meant G right there. It's just that the integral, so in this case from 0 to 5, acceleration, integrating acceleration gives you velocity. equals the v of 5 minus v of 0 as initial. And so rearrange that the velocity at 5 seconds is equal to the initial velocity plus the integral from 0 to 5 of 8 of t dt. But then looking at this, right? Area under this curve is a triangle, so I'll use 1/2 base times height. So the base is 5, the height is 20. 5 times 20 is 100. 1/2 of that is just 50. And then I'm just going to assume that the initial velocity is 0 because it's never stated anywhere. So I'll just say that v of 5 is equal to 50. And then since this is velocity, it has to be positive because velocity is a vector. And then going on with that to part H, asking to use the v of t function derived in part F. So I'll say v of 5 equals 20 5 minus 2 5 squared. So v of 5 equals 100 minus 5 squared is 25. 2 times 25 is 50. So v of 5 is equal to 50 meters per second. Positive. And yeah, it's the exact same thing. Doing part I now. I asked for the function for the position. And so position is the integrating velocity gives you position. So I'll integrate the v of t function given I got before. So I'll say x of t is equal to, so this is going to be t squared divided by 2. This is 10 minus, so this would be t cubed divided by 3. So negative 2 over 3 t cubed. And then plus c. But then we don't really know initial position. So I'm also just assume it's 0. So the x of t equals 10 t squared minus 2 over 3 t cubed. Alright, moving on to part J now. Let me just paste this graph in here first, real quick. A little bigger to easier to see. So part J. Part J, it's asking to the position versus time graph. So I'm gonna say this is t. I'm gonna say this is x. I'm gonna graph 1, 2, 3, 4, 5 for seconds. The position I'm gonna say 40, 80, 120, 160, 200. Say that because the final position at 5 was about 167, so I wanted to go a little bit over to make the graph a little bit easy to see. So the initial position I'm assuming starts at 0. Position at 1, plugging it in to the x of t function, it's about 9.33, so I would say it's about like right there. At 2, it's about 35, so I would put it about like right there. At 3 seconds, it's about 72, so I would put it like here. At 4 seconds, it's about 117, so I'll put it around there. Then 5, it's 167, so I'll put it about right there. So drawing this line through here, I'm gonna do my best right now. It would look a little something like that. Let me redraw that real quick. That is not the best line I could do. So that. It's a little straight in the middle. Should be a little bit more curved, but I try my best. And then now the first part asks to find the instantaneous velocity. Draw a line that represents that. So at 2 seconds, I'll just draw the tangent line because that represents the slope of that, which is the derivative. The derivative of a position is velocity, so that's instantaneous velocity. I want the average velocity from 0 to 1. So I'll draw the secant line from there. That is not a secant line. That is a secant line right there, about. So that's the average velocity, average speed from 0 to 1. And then average speed from 0 to 2, just like that. And then the average speed from 0 to 3 looks like that. Average speed from 0 to 4 looks like that. Last part, I have to explain what happens to the average speed from 0 to 5. And the average speed increases. Average speed would increase because from 0 to 5, the line for average speed looks like that. And as you can tell, it kind of is way steeper than before. That's one way to tell. Another way to tell is that the velocity and acceleration are pointing in the same direction. They have the same sign. So velocity is increasing throughout this whole motion. And so from 0 to 5, velocity is always increasing. So the speed has to always also increase. Yeah. Alright, so for the last part, K now, just ask for the average velocity between 1 and 3. So the average velocity can just be found between this delta x, displacement over time. And so in this case, it's just going to be x of 3 minus, x of 1 over t. And then x of 3 is 72. X of 1 is about 9.33. T between 3 and 1 is just 2. So this is just equal to 62.6667 over 2. Putting to your calculator, it gives 31.333 meters per second. Plus, because velocity is a vector, and it's going to the right still. So plus, that's your average velocity, 31.333. Thank you for watching this video. FRQ number 2 is now complete.